Okay, so the next presentation comes from Technica. So we have two people presenting this topic. The one and only Lars Völker and a colleague Regina Leis. Yeah. So Lars, I think everybody knows him. He's joined BMW in 2010, worked on internet since then. He's the main author of SOME IP protocol. And since 2019, he's a technical fellow at Technica Engineering, where he supports OEMs and tier ones to do better Ethernet in their car. And he's heavily involved in the Open Alliance, so working in different technical committees, TCA 17, TCA 19. Okay, and her colleagues, so Regina Leis. So she joined System Engineering of Technica in 2023. She has contributed to multiple projects and managed multiple projects with OEMs related to layer 2 switches and AVB and TSN. And currently, she focuses on management and monitoring of Ethernet switches. So really the goal is to optimize the communication interface between switches and hosts. Okay, so the stage is yours now.
Thank you very much. So, the structure of our next 20 minutes is as follows. First, I will start off with the motivation behind our concept. Lars will then present the design of our security solution for SOME IP and how we could protect messages. And finally, we will end everything with a short summary. So let's start with the motivation. On the right side, you can see a typical ECU with an Ethernet switch and a host controller. Both of them need to communicate with each other to manage or monitor the switch. Let's call this connection the switch management interface. Over this interface, we have different topics that could be covered. For example, cable diagnostics, link up of the ports, drop counters or address table, changing the VLAN configuration or just reading it. And for security, we might want to activate MACsec or install some keys inside of the switch. The switch management is not yet standardized for automotive. With OpenTC19, we as Technica want to change that. And the goal is to have everything vendor-specific on the side of the switch and everything OEM-specific, such as diagnostic jobs and DTCs that are related inside of the host. Here in this next picture, we added a bit more details and an example how this could look like. So we again have an ECU with a switch and a host. On off-port side, we have some configurations. In this example, we are showing Flink, which is the network configuration model from Technica. At this point, I don't want to give too many details here, so we are focusing on the right side, and especially the light blue part. So in this example, we are showing a host ECU with an AutoSAR Classic platform. And inside, we have a switch manager that is communicating with some type of switch agent inside of the switch with a protocol that is not yet defined, at least for the standard. And yeah, we have different options for the standard. We could introduce a new protocol. But this is followed by a lot of challenges. For example, we need a lot of new tools and processes. We need to build a lot of know-how for everyone involved. And in the end, it's a completely new ecosystem. So we at Technica and also other companies propose to use SOME IP for this switch management interface. But yeah, now the question is if that is even a better fit. SOME IP is supported on all major ECU platforms, and it's already deployed by many OEMs worldwide. So it's over 10 years in series production and shipped in millions of vehicles. And if we make use of the service-oriented approach, it's way more cost-efficient and can be rolled out today. The only thing that is missing for this management not only for some IP though, also for other protocols, is a good security solution. And especially two questions. On the one side, how to install keys for MACsec and MKA. And on the other side, how to protect the messages. And here, I will hand over the word to Lars, who will show us our design.
Thank you. So we're trying to figure out what we want to do, right? And if you look at that, one of the things we had to do is basically we have to supply keys to MACsec, right? For security, that's one of the biggest important use cases because we need to do securely that, right? If we do not have a secure key installed, then of course everything else is not secure afterwards. So if you look at the right-hand side, you can see the typical key hierarchy of MKA, and that you have probably seen that before, at least if you listen to a presentation of ours presenting MACsec. But what's basically key information here is you have more persistent key, long-term key, and that's called CAK, the Connectivity Association key on the top left, which has to be securely stored. That key has a name. You can think about it as like an ID or label, so you know which key we are talking about. And then, of course, we are using the key. And we want to do two things here. We wanted to basically make sure that messages being transported for the key exchange protocol of MACsec, that is MKA, that those are protected. That's what the AAC-MAC in the lower left corner is for. And for that, we use a key called the integrity check key, ICK. In order to generate that, we just use the regular CAK, use a KDF, and then calculate it. That's basically a one-way function, right? You can go down, but not up again. And the second key we generate is the so-called key encryption key. And that is a key we need to use for encrypting a session key that MACsec uses, the SAK, so the secure association key. You probably have heard about that before. So basically, you can think the SAK is the key that MACsec uses, and the CAK is what the key exchange for MACsec uses to establish that key. So that's what MACsec does, right? Now, we have to figure out how to securely get those CAKs into the switch, right? Because we want to run this MKA and the MACsec inside the switch silicon. So how do we do that? First of all, we have a host also in the ECU, or have somewhere a host controller, and that host controller has probably some way to receive the key, which is usually OEM specific, proprietary, but there we have the key. We could unpack it and send it over now to the switch. But do we really want to do this in clear text? No, we don't, right? This would be unsecure. And do we really trust completely that software stack? No, we don't, right? We don't trust the whole host stack because maybe it's a head unit with an Android operating system or something. So typically what we want to do is we want to use the HSMs inside the chips. So we have the small HSM, the hardware security module in the host, in which we unpack the key which we want to install, and then we need to transfer it over to the HSM and the switch silicon, where we then use it later for MKA, so for MACsec. So when we do that between the HSMs, of course, it's clear that we cannot use just like transport security. Like if we would use MACsec or TLS or IPsec, then of course, or SSH for instance, right? Then of course it's not really secure because now we would either need to implement the whole stack in the HSM, but people wouldn't do, or we have to hand the key down to the stack which we don't trust and then transport it over. So we were thinking there has to be something a little bit more efficient and a little bit better to do. And one more thing is that we wanted to minimize the algorithms and the crypto we need to implement on the switch. Because we have never enough resources, right? So we wanted to make it simpler, like having less crypto algorithms, less things here in order to make sure that it's easier to validate the firmware of the HSM, because that is really security critical to make sure that it's really secure. So what would be the case, what we think is, why don't we reuse what we have already, right? In MKA, I said before, we have for at the bottom left, we have this ICK. And we use that for a CMAC to generate the integrity check for the messages, right? We can use something like that. And we can also use the key rep to securely transport keys over to the other side. So why don't we just try to reuse the crypto? So what we could do is the following. We have on the left side still MACsec in green. And on the right side, blue, we create something very similar. We use the same crypto, we use the same key hierarchy, and basically, we do basically the same thing again. Like let's say for the time being, something like MKA to establish the key, that MKA uses to establish the key for MACsec. Sounds like we stacked the same thing 2 times, but you have to keep in mind that the MKA runs at every startup, while this key installation into the switch silicon will be done like in production of the vehicle and in service. So very seldomly. So they're not running all the time, both of them at the same time. So the CKN, we could just have an ID. We can also use a CKN, but in order to not mix that up, we give it a new name. We call it ID, AB, or whatever you want to. And we have this pairing key, which is then what the CAK was, like a long-term secret. And we have then as well a KDF, breaking it into 2 keys, an ICK and a KEK again. And we can use those like before, protecting messages and encrypting keys to transport them protected. And that allows us now to establish one or multiple keys. We can give them a number. We could also give them a name, but we figured out, like, number is probably good enough because we are not using like so many keys that we are like, have there need a complicated process. So what we will have is like a CAK per switch port. Maybe you use some additional keys for some management features or something else. So might be a couple of keys, maybe 20 at most. Maybe it's 25, I don't know, but we're not talking about thousands or something. So in the ECU itself, right, if we build both of those chips in the same ECU on the same PCB, we can assume that this pairing key and this identity is static. Right? It doesn't change because those chips are sold on the same board. They trust each other. And so basically, we have to figure out how to install them, but that's kind of a production process of the ECU. There are some solutions and proposals for that, but this is the part I want to skip here. But you can think about that. There's, depending on your attacker models, a few easy solutions out there. So what we do now is we use like basically the same key hierarchy and crypto like MKA because that's already available. It's something we understand. We have validated code for, but how do I now tie this together, right? How do I use this key now for MACsec? And basically, it's very simple. I do the blue exchange like when I build the car, or when I service it by replacing an ECU. I install on both ECUs that are on an Ethernet link the same CAK. That is something OEMs can do today, and then basically, the way I do that, I transport them over this new blue solution we were just saying, like, same key hierarchy, long-term secret, and then wrapping it up again. So the question now is, how does it really work, right? This is just a key hierarchy in crypto. We need to build a protocol around that, and that's what we want to look at. So you see the messages. We have 4 simple messages in the middle. We basically do like kind of a 4-way key exchange protocol. And what we need to do is way less than MKA. The reason for that is MKA needs to be pretty dynamic, supports different options, could be using having like a multi-trop bus with multiple participants that have to talk to each other. We don't need that. It's like just 2 of us, right? So we need a simpler protocol, or we can use a simpler protocol. So in order to do that, we are basically doing something very simple. The first message on the left, you can see we send the ID. So we are sure we're talking about the same thing here, using the same key. And we are putting in a random number, like the crypto guys would say, like nonce, right? So then we have a sequence number, because we don't want replay attacks, so we want to number our messages. And we basically put that also there and start with counting by 1. Status of the message, since I'm sending the first message, probably okay. And then at the end, you see there is this integrity check value. That is the cryptographic part that makes sure that nothing of the message was changed, and that also the message is tied to that key. And since it's only 2 with the same key, I know if I didn't send it, the other guy sent it, and I'm receiving it. So everything fine. We have the first message. We send that out to the switch side, so the responder side. And now the responder is doing the following. It checks if this identifier makes sense for him. If it doesn't know it, select a key with it, can then check the ICV, can check if the sequence number and nonce are known. If not, then you can install them, save them away, and answers the message. And you see this on the bottom right, this black box. This is the format for the way back. What do? Basically the same as the initiator, right? We are getting in there like another nonce, because we have our own basically random number, and we have also a sequence number for the other direction. Also put that in. We start with 1. We reflect back what the other guy sent us before, so he knows that we are alive, because if I'm sending now this message protected by the ICV, and it's the same nonce as the one I got in the first message, then the sender, in this case the host, when receiving it can say like, okay, that's the same number, the sequence number, everything adds up. So yes, the guy is really alive, it's the guy who has the key, so it's not a replay attack. So we already are now have figured out how to do a replay protection, and we also know that's the right key, so we can trust each other already a little bit. What's the next thing we want to do? We install a key, right? That's why we're here, right? We want to install the key. And how we do that? You can see then in the first message, we are basically sending the same information again. Of course, sequence number are incremented. And we then basically wrap the keys, put them in an array of keys, give them each key a number. And then also like the type, how we wrap them, because it could be different algorithms we could use for wrapping. We could AES-256, maybe 128 is enough, or maybe we find something better. So, we should probably tell them what algorithm we want to use. But at the end, we send that over, and now the switch will unpack this key or multiple keys, unwrap them, and of course, before checking the messages, checking that if you unwrap them, that's okay, if everything is fine. And then if everything was fine, you install the keys and send back, hey, I have installed the keys now, my HSM. Everything is good here, and they come back. And so this is like a very simple way how we can implement the very simple key exchange. Some parts, like I said, key hierarchy algorithms, is very similar to MK. Everyone has implemented it. And if you look at, for instance, like the nonce and sequence numbers, you could argue that the nonces are a little bit like the MIs and the sequence numbers a little bit like the MNs, if you want to say so. But it's it's some similar concepts, but a little bit simpler and different, more like IPv2 at some parts. So what could we do with this key? We can install it for MACsec, right? For every port, another CAK. So we have a way now to securely install that. So we can do something else as well. So we can also try to protect some messages here. And we are thinking it might make sense that on some IP you're not using MACsec or TLS or SecOC. No, not TLS or IPsec or MACsec in this case. And we could use a key here to protect the some IP messages. And if you want to integrate that in a classic AutoSAR platform, you cannot really come up with something completely new. So you have to pick something existing. Since I'm in the HSM, really do not want to implement full TLS because way too much complexity, way too much potential problems. So why don't we do something simple and reuse the way that SecOC is integrated in AutoSAR, classic AutoSAR, right? It's very simple way where we basically only need a bit of information that is a sequence number, and that's an integrity check value. And what we basically do, we attach to the bottom of the some IP message a small security header that protects the whole message, has in addition an ID, a key number, because maybe we want to rekey. Probably not, but who knows what happens in the future. And then we want to see the direction, because we want to use the same key for both directions. So we flag for direction, sequence number, and then the ICV at the bottom, right? And that is something that was pretty easy to integrate in today's SecOC in AutoSAR instead of something new. But this could be something very simple we could use to protect some IP messages. So, I think a couple of years ago I said, we don't need a special some IP security solution. So if you remember that, I'm sorry, I was wrong. But we might need it. I mean, it might be a good idea, right? It's basically, I gave you now a key exchange for SecOC, and use something like SecOC to protect some IP. So it's not quite a new thing, but a little bit new. Hope that's okay. So let's go back to the diagram Regina showed us. We can fill out now some spots. Let's assume we do the management with some IP, which is one proposal, like Regina was saying, that a couple of people in the TC19 stated. So this is basically then the way to transport between the switch manager and switch agent information. So in order to protect them, on the switch itself, we have this little security module below the switch agent that does our crypto now. And on the right-hand side, we have the SecOC module, which protects the communication over there. And then, of course, we have some key exchange modules here in the HSMs. And you can see all the new stuff, or the stuff we discussed is light blue, right? We're going to only look in those light blue parts. Maybe it's easier to see. And at the end, it's pretty easy to integrate that. A pretty straightforward solution, and you can basically run it today. I mean, you have to write a couple of lines of code for the key exchange. We have done that, but it's not that difficult. It's easy to do. And that's how we would integrate the security and the key exchange here. So let's go to the summary. What have we done? So we have basically, or Regina has basically shown us, that it's an interesting idea to look into as managing a switch via some IP, because it's everywhere already, right? Ecosystem is established, you get it for free, right? Every stack vendor has it. We have also said that if we do that, we might need a little bit of additional security. One of the things is we need a small key exchange, because having, like some people do in CAN, like a key for a very long time and using always the same key is not really the best approach here. But maybe we want to use for some IP messages like a fresh key, like we do on MACsec and other solutions. And also we need to be able to install CAKs, right, for MACsec, like we said. So for that we can also use that key exchange protocol, as it gives us a good solution to basically tunnel keys from between two HSMs and minimizing the attack surface here and the complexity of the HSM. So what's some of the advantages for the implementers? The crypto is already there, right? And if the stack supports some MK and MACsec, you have the crypto already implemented. It's already available. You have the libraries. You can use it today. And of course, we have done, of course, the key securely in the HSM, what is what we want. And I wanted to add one more thing, and I didn't write it yet, just as a reminder. We are currently writing a specification for that. We want to publish that for everyone to discuss, because we do not think that it will be perfect if we write it alone. But we are very happy if some people volunteer to discuss this further with us. And like I said, we try to create a specification that then everyone can read. But it probably takes a little bit longer. It's probably not a Christmas present, maybe a little bit later, but we'll see. And with that, that was our presentation. I thank you for that, listening, and we are ready to answer some questions. No.
Okay, so thank you, Lars. Thank you, Regina. So we have some questions. Yeah, of course.
Thanks, guys, for giving the talk. I need a history lesson here, Lars. I seem to remember that when we talked about SECOC, there was a requirement to put the SECOC ICV, quote unquote, in the beginning of the message, because otherwise we would be violating the rules for actually changing a some IP message and adding at the bottom. And now we're adding something at the bottom, the ICV, where it actually belongs. It makes implementation way easier. What did we get wrong when we did the SECOC and put the thing on the top?
Are you mixing up the end-to-end header with the SECOC header?
Same problem, shouldn't it be?
Yeah, but that's what we did for end-to-end header. We put it to the front.
So why can't we put that at the bottom?
We decided back then, because back then as we designed it in AutoStar, we said it might be easier to extend the message later.
Exactly.
So are we with an unprotected part, but it at the end it's doesn't make a big difference, it seems.
Okay, cool. Thanks.
Thanks.
Yeah. Sorry, mic is very low. So you said, I'm referring to the switch management interface you were pointing out. You said we have some IP, and so we basically have it. We can just use it, and it's done. That was the statement. So for me, okay, if you have some IP, you have a way to talk to the agent, but actually the content and what you communicate to the agent is the important thing. We have standards for that already, and so why should we not look at those?
No, I'm not saying that you cannot look at things, right? I'm just saying there's a proposal here where the integration into the existing platforms is done. The ecosystem is done, the know-how is done. And what you have to do in addition, you have... Say again?
Just for the communication. For
yes, for sure. And if you refer to CoreConf, you can transport the same as CoreConf over some IP. It's very simple to build a service to do that. Not sure if it's a good idea, but possible, right? You can design something else. It's understood, right? We have the processes for that. Yes, it is not that we have published that, how we would do that. I mean, if you were at the booth, you might have seen a little bit of that. I'm not sure if it's, if you run out now, oh, Carl, sorry for that. You might still see something, but yeah. So you need to do a little bit more to design that, but that's a process that, is understood, for sure. think it's Friedrich now. You're all in the dark. Why do I have to stand in the light where it's warm and you... Go ahead.
So thanks for the presentation also from my side. We already discussed yesterday a bit, like crypto is the art of turning any problem into a key management problem. Now you shifted that problem a bit to injecting the key, the initial key to run your key agreement protocol and the protection of this. So this needs to be discussed as well, I think. And what you sketched yesterday to me, maybe you want to repeat it in a few minutes, is that this works probably in the system that you showed, where everything is inside the ECU, and this is like the host microcontroller directly connecting to the switch. But what about use cases that would require remote switch configuration? There, this is maybe a bit more problematic because then you have to send this via the in-vehicle network, and then that's still a problem, right?
So the messages we designed here, if you send them over the in-vehicle network, it's fine. Right? We designed them that it's fine. The problem you're having is that the first key to bind those two ECUs together, how to inject that. And today, typically, this is very proprietary. And I know that Harry was pushing for that in TC17, where we together share the MKA part. And he was saying, like, we should probably look into that, right? We have done something for ASA to do this like per device, and we could reuse some of those concepts. But that is something where today everyone has a different solution, right? And that is kind of the issue here. We could propose something, but I was a little bit hesitant because everyone has something already. And if we have n solutions, want to get down to one, adding another one is n plus one, not necessarily one, right? So that is something either we figure out that the ASA concept can be adapted, Harry and I come up with a better idea, or even better, the group comes up with a better idea, or we have someone who has something that's really cool and wants to volunteer to show that.
Okay, thanks.
Yeah. And from the discussion from yesterday, so what we were saying is inside the ECU, it's very simple to establish the same key. It's only if it's inside the network, right? Then it's getting more difficult because inside the ECU is produced by one tier 1, then the tier 1 can securely create that key in both ECUs, like with an anonymous Diffie-Hellman exchange, or you inject it in both, right? It's easier than if it's two different ECUs of two different manufacturers. Yeah. Oh, yeah.
Yeah, I just wanted to be sure to understand correctly. You have actually two proposals, right? You have this one simplified protocol to exchange the key, to put the key into the switch.
Yes.
And then the second one, which is actually securing SOME IP once you have this key. Or are they connected together, these two proposals?
No. There's two proposals, two parts of the puzzle, right? Two puzzle pieces. As Rudy correctly said, like everything is key exchange at the end, right? If you don't have the key, you cannot do anything. And what we're doing is we have the key exchange that can supply the keys for MK and also for protecting some IP messages. And you're right, that is the second piece of the puzzle. That was the slide which I can jump back. So it was only one slide where I just sketched a little bit how this would work, and I did not, discuss all the details because some of those are still things we are discussing, some corner cases. But basically, the layout could be something like that. You could probably make this a little bit simpler, I guess.
So would it be correct to rephrase one of the proposals that you are proposing to use a configuration interface of the switch, which is exposed to the network and which is based on a protected SOME IP?
That is what we are looking into. It was not proposed by us, but by multiple companies in TC19. And we are trying to figure out if that's okay. Because one of the things, surely, SOME IP cannot protect itself. And putting TLS below it is not a good solution.
Okay. Yeah,
so we are trying to figure that out. Thanks. Oh, Harry.
Just wanted to extend Friedrich's question. That part related to if it's an extended ECU, or that's still part of the objective in our TC17, so we haven't quite finished that yet.
Yes.
That's all.
So in TC17, what I was saying, basically the 10-base T1S is kind of something we hope to figure out like a month ago, which is very hard, and then the next step would have been like a bridge device, like, you think about like a bridge from Ethernet to CSI2 or something, for instance, and how to get keys into that, yeah. Josecho.
Thank you, Lars. Thank you for the
I should have had more slides that you asked that question.
I don't think I really understand everything, but let me ask you one question. Let's see, we have one host controller that is secure and trusted inside the car.
Yeah.
And then you have the switches you want to put. So why we cannot relate to something simple like by network configuration open a VLAN only between those two elements, and then give the keys between this secure host that is trusted because he received the MKAs by the offboard, and then the switch with this VLAN that protects any intrusion from something. I think it's not going to protect physical attacks, that's for sure, but perhaps other kind of attacks he will protect. So what are the missing pieces for this? I think simple solution. Yeah.
So the question is how much security you want, right? I mean, if you want to install MACsec keys into the ECUs to protect Ethernet with MACsec, then I would assume that you want those keys to be a little bit secure so that you really protect something, right? Because if I'm there and can read what key you installed, then I can talk to your MACsec ECUs and see everything and can change everything, right? So what we are saying is basically we are afraid of the use case you bring the car to the service, replace an ECU, and someone could be attacking the communication that in a service you're supplying the keys to pair this host or hosts together with the switches, right? And while, it is not the scenario that happens every day, but it's possible, right? Because it's a car of like some customer drives it to a service, maybe he has manipulated a little bit, you replace an ECU, install the keys, and now he has on his device all the keys and can now start manipulating your car. Maybe getting some features he didn't pay for, maybe doing something crazy, I don't know, right? But it depends at the end of what your threat analysis tells you. If you're saying, I don't care, then, question is if you need MACsec then. And then if you don't need MACsec, you don't need a key for that. Maybe for the management, you don't need a key. It's a fair discussion. And also the other thing is if for the switch management, we would be only monitoring and not really changing something in the switch, then you could always discuss, do we need security at all, right? It's a fair discussion. We're just trying to give us options in order to go forward.
Okay, thank you.
Yeah.
Okay, I think we are late for the
There's one more question.
Okay.
Carl, do we get one more question? Yes, Carl says yes. Go ahead.
Thank you for the presentation. So you said over here there were kind of two proposals, right? The first one is to install the keys into the switch.
Yes.
And then there is using it for some IP. So that the first piece couldn't that also be used for the core conf Yang proposal? To install the keys into the hardware. You
can use it for everything, right? It's so just, I mean, as long as symmetric keys like AS keys are good, sure.
So your proposal, that piece of your proposal could be used for the alternative being discussed in TCP.
I mean, it depends on how you want to protect Yang. If you want to go for full-fledged TLS, then you can also use symmetric keys. You could do that. It's overhead-wise. Maybe not perfect, but yeah, sure. Technically that works. And like I said, the keys could also go in MKA, and MKA uses it to do MACsec, right? Yeah. How you use the keys is up to you. You can maybe have a very cool another protocol, and that can use AS keys. Sure.
Thank you.
Thanks.
Okay, thank you, Lars and Regina.